In the last lecture, we were examining the conservation equation in a spherical coordinate system. As I had explained, the spherical coordinate system, there are three coordinates r, theta and phi. Okay. The radial coordinate r is the distance of the location from the origin, okay, the distance in from the origin, which is square root of x square plus y square plus z square. Theta direction, theta coordinate is an angle. It is the angle made by the position vector with respect to the plus z axis. So, theta is equal to 0 on the plus z axis and it is equal to pi on the minus z axis. Phi is the angle made by the projection of the position vector onto the xy plane, the angle made by that projection with the plus x axis. So, phi is equal to 0 on the plus x axis and it is equal to pi on the plus y axis and so on. Okay. So, r is always positive because it is a distance. Theta varies between 0 and pi and phi varies between 0 and 2 pi. Okay. Now, locally the orthogonal coordinates, the unit vectors locally at each location, there are three unit vectors, one along the r direction, one along the theta direction and one along the phi direction. And each of these is in the direction of increasing coordinate. The unit vector in the r direction is along the direction of increasing r. The unit vector in the theta direction is along the direction of increasing theta, and the unit vector in the phi direction is along the direction of increasing phi. These three unit vectors are perpendicular to each other at all locations in space. The direction of the unit vector changes as you change different locations in space, but at a particular location in space, the three unit vectors are all perpendicular to each other. Okay. To derive a balance equation, we had constructed a differential volume between two surfaces perpendicular to the r direction at r minus delta r by 2 and r plus delta r by 2, separated by a distance delta r. Two surfaces in the perpendicular to the theta direction at theta minus delta theta by 2 and theta plus delta theta by 2, separated by a distance r delta theta, because theta is an angle. So, the actual distance is the radius, the distance from the center times the subtended angle, and two surfaces at phi minus delta phi by 2 and phi plus delta phi by 2, separated by a distance r sin theta delta phi, okay, because the actual distance travelled in the phi direction is equal to the radius vector r sin theta in the xy plane times the angular increment, the increment in the angle. Okay. So, therefore, the distance travelled are not the same as the increments in the angle. Okay. They are equal to a scale factor times the increment in the angle, okay, as shown over here, where hr, h theta and h phi are the scale factors which multiply the increment in the coordinate to provide the actual distance travelled. Okay. So, then we had characterized the surfaces of this differential volume. Surface at r minus delta r by 2 is the two increments perpendicular to the r direction, h theta delta theta times h phi delta phi at r minus delta r by 2, and at r plus delta r by 2 it is the same, h theta delta theta h phi delta phi at r plus delta r by 2. Important point to note, h theta and h phi do depend upon r. Okay. So, they are not constants, and therefore, these do depend upon the coordinates, the surface areas of the different surfaces. Mass conservation equation: change in mass in time delta t is mass in minus mass out plus production of mass in time delta t. Change in mass in time delta t is equal to the volume, okay, HR delta R H theta delta theta H phi delta phi times the difference in concentration between the times T plus delta T and the time T. Okay. The mass in at the surface at R minus delta R. Okay. Mass is coming in at the surface if the flux Jr is positive. Okay. So, a positive flux, okay, results in an increase in mass within this differential volume if it is in the plus R direction. Okay. So, the mass in is equal to Jr times the surface area of the surface at R minus delta R by 2, which is H theta delta theta H phi delta phi. Okay. This flux that I had written is only the diffusive flux. Okay. The total flux actually consists of a convective plus a diffusive part. Okay. So, I should actually write this as C V R plus J R. Okay. The sum of the convective and the diffusive fluxes. Okay. C times Vr, concentration times the velocity perpendicular to the surface. Okay. At the surface at R, the velocity perpendicular to the surface is in the plus R direction. Okay. The velocity perpendicular to the surface is in the plus R direction. So, C Vr plus Jr, the diffusive flux, times the surface area. Okay. H theta delta theta times H phi delta phi. Okay. The mass out at R plus delta R by 2 is similar. Okay. Okay. C V R plus J R, okay, times H theta delta theta H phi delta phi at R plus delta R by 2. Okay. Mass in at theta minus delta theta by 2 is equal to the total flux that includes the convective and diffusive parts. Okay. C V theta plus J theta, okay, times the surface area, which is HR delta R H phi delta phi, okay, at theta minus delta theta by 2 times delta T. Okay. Similarly, the mass out at theta plus delta theta by 2 will contain the convective plus the diffusive part. Okay. Times HR delta R H phi delta phi. Okay. And similarly in the phi direction. Okay. Including both the convective and the diffusive parts. Okay. Okay. Times the surface area of the surface perpendicular to the phi direction, which is HR delta R times H theta delta theta. Okay, is the surface perpendicular to the phi direction. Okay. The rate of production. This is equal to S, which is the mass produced per unit area per unit time. Okay, S is the mass produced per unit area per unit time times the volume. I am sorry, S is the mass produced per unit volume per unit time. Okay, this is the volumetric production rate. The mass produced per unit volume per unit time times HR delta R H theta delta theta H phi delta phi times delta T. Okay. S is the mass produced per unit volume per unit time. So, it is multiplied by the volume and multiplied by time. Okay. Okay. So, now we have to put all of these together. Okay. On the left side is the change in mass in a time delta T. Okay. That is HR delta R H theta delta theta H phi delta phi, okay, volume into the concentration at R t plus delta t minus the concentration at r theta phi t. Okay. That is the change in mass in a time delta t is equal to the mass in minus the mass out at the two surfaces. Okay. At the surface at r minus delta r by 2, the mass in is equal to C Vr plus Jr into h theta delta theta h phi delta phi. Okay. At the surface at r minus delta r by 2, okay, times delta t. Okay, that is the mass in at the surface at the inner surface at r minus delta r by 2. Okay. Okay. Mass out at the surface at r plus delta r by 2. Okay. So, this is equal to C Vr plus Jr times h theta delta theta h phi delta phi at r plus delta r by 2. Okay. That is in the r direction. Similar equations in the theta and phi directions. Okay. So, C v theta plus j theta times the the surface area perpendicular, which is the product of hr delta r h phi delta phi. Okay. The whole thing at theta minus delta theta by 2 should be a delta t here. Okay. Flux multiplied by surface area multiplied by the time interval is the mass in and out. Okay. Then similarly in the phi direction. Okay. Okay. The surface area perpendicular to the phi direction is hr delta r h theta delta theta into delta t. Okay. Okay. And finally, the volumetric source S hr delta r h theta. This is the balance equation. Divide throughout by volume and time interval. Okay. Divide throughout by volume and time. That is, volume is hr delta r, h theta delta theta, h phi delta phi. That is the volume, and time delta t. Okay. If you do that, what you will get is C at r theta phi t plus delta t by delta t. Okay. On the right side, I divide throughout by delta t, hr delta r, h theta delta theta, and h phi delta phi. Okay. So, what I will get is 1 by hr h theta h phi, okay, into, okay, C Vr plus Jr, okay, into h theta h phi. Okay. The whole thing at r minus delta r by 2. Okay. minus C V r plus J r H theta H phi, okay, at r plus delta r by 2, okay, whole thing by delta r, okay. So, recall this relation here, okay. So, I am dividing throughout by delta r, delta theta, delta phi. The delta theta and the delta phi will cancel out. I will get only a delta r in the denominator times in the numerator C V r plus J r into H theta H phi at r minus delta r by 2 minus the same value at H r plus delta r by 2. Okay. The whole thing divided by delta r. Okay. And it is important to note here that these things H theta and H phi are actually functions of r. Okay. H theta and H phi are functions of r. Therefore, we cannot just cancel out H theta and H phi between the numerator and the denominator. Okay. That is an important point to note. If you recall, this arises from the fact that the surface area is a function of position. The total mass transfer is the flux times the surface area. In a Cartesian coordinate system, the surface area is not a function of position. Therefore, we could just cancel these out. The scale factors were all 1. In this case, the surface area is a function of position, and therefore, we cannot cancel out the HR and H theta and H phi in the expressions for the surface area, because they are different on the inner and the outer surfaces, on the two surfaces. Okay. So, that is the first term. Okay. The second term is going to be equal to C V theta plus J theta into HR H phi, okay, at theta minus delta theta by 2, okay, minus C V theta plus J theta HR H phi, okay, at theta plus delta theta by 2, the whole divided by delta theta. Okay. This thing comes about from the second term here. Okay, this thing comes about from the second term here. Okay. I divide throughout by delta r, delta theta, delta phi. Delta r and delta phi will cancel out. There is still delta theta left behind in the denominator. And I have C V theta plus J theta times HR H phi. Okay. The difference between those two at the two different locations. Okay. And the final term is C V phi plus J phi times HR H theta at phi minus delta phi by 2 minus C V phi plus J phi times HR H theta at the location phi plus delta phi by 2 whole divided by delta phi, okay, plus the source term S. Okay. So, this is the complete equation, and now we have to take the limit as delta t, delta r, delta theta, delta phi all go to 0. The left side is just equal to partial c by partial t. Okay. On the right side I have, okay, 1 by HR H theta H phi, okay, into minus partial of C V r plus J r times H theta H phi by partial r. Okay. Minus because I am taking the value at r plus delta r by 2 minus the value at r minus delta r by 2. I am sorry, this is the difference between the value at r minus delta r by 2 and the value at r plus delta r by 2. whereas the derivative is defined as value at r plus delta r by 2 minus the value at r minus delta r by 2. That is why I have a negative sign. The other important point to note is that I have to take the derivative of this whole quantity, which includes the flux times the surface area, and surface area is h theta times h phi. Okay. So, I have to take the derivative of the whole thing. Okay. The next term minus partial of c v theta plus j theta h r h phi by partial theta, okay, minus partial of c v phi plus j phi h r h theta by partial phi plus s. Okay. That is the conservation equation. Okay. Now, I can substitute, okay, h r is equal to 1, h theta is equal to r, h phi is equal to r sin theta, okay, for the 3 scale factors. Okay. So, partial c by partial t is equal to 1 over r square sin theta, okay, into h r is 1, h phi is r sin theta. So, I will get r sin theta here. Into r by partial phi. And when I take the derivative in the first term with respect to r, I can cancel out sin theta. When I take the derivative with respect to theta in the second term, I can cancel out r. Okay. And my equation will become 1 by r square d by dr of r square into c vr plus jr plus 1 by r sin theta partial of I should have a minus sign in the beginning. Plus s. Okay. That is the conservation equation in a spherical coordinate system. Okay. As is usual, we can take the convective term to the left side and the diffusive term on the right side, and we will get partial c by partial t plus that is equal to minus plus the source term. Okay. That is the conservation equation in a spherical coordinate system. Now, for the flux we can write down the constitutive relation. Okay. For the flux we can write down the constitutive relation J r is equal to minus d times partial c by partial r. The change in concentration when you move a small distance in the r direction. Okay. The flux in the theta direction is equal to minus d partial c by partial theta is not correct, because theta does not have dimensions of length. When you move a small distance, when you increment the angle theta by a small amount delta theta, the distance moved is r times delta theta. Therefore, the flux has to be equal to minus the diffusion coefficient into the difference in concentration by the distance moved, and that distance moved is h r times delta theta. Okay. Okay, that is the expression. Okay. Similarly, in the phi direction, the distance moved is d by h phi delta phi. Okay. Okay. Or I can write this as minus d by r partial c by partial theta, because h r is equal to r and this is d by r sin theta. So, those are the increments. Okay. Substitute that into the equation. Okay. Substitute that into this equation. Okay. Be in r, I am sorry. Substitute these expressions, okay, for the fluxes over here. Okay. Okay, to get this is equal to, on the right side, plus the source. And finally, we can simplify this for the case where the diffusion coefficient is a constant. The right side will just become equal to d into 1 by r square d by dr of r square 1 by r sin theta. Made a mistake here, I have not included the sin theta inside this. So, over here there is a sin theta, which is due to this term here. Okay. these two factors of 1 over r, I can take it outside to get a 1 over r square here. So, that is what you get when the diffusion coefficient is a constant. Okay. So, this is the mass conservation equation when the diffusion coefficient is a constant. If you recall, when we did the Cartesian coordinate system, we derived the mass conservation equation, and then I had got the mass conservation equation for you in vector notation. The same thing we will do in this particular case for a spherical coordinate system. So, I will continue this derivation in the next lecture and define for you what are the vector operators in a spherical coordinate system. I will continue this in the next lecture. I will see you then.